Good evening, all of you. My name is Anil Yadav. So this is the 10th tutorial on fundamentals of semiconductor devices. I think if you have any doubts, you can ask me or we can start then. Sanjeev asked some doubts. Okay, Somnath, I think, asked for some doubts. Okay, we can wait for you. So today we will be actually today we will revise some of the concepts on continuity equation and some graphs on that. We will see that.
Hello,
Hello, yes, Somnath.
sir. mm,
Yes, Somnath.
Please start, sir. Actually,
Okay, okay, let us start.
my mic is not connected, sir.
Hmm?
My mic is not connected still now, but now it is available, sir.
Okay, okay. You had some doubts. Can you ask now, or can we start? We can
Sir,
start.
actually, sir, I think, sir, the course will be as the course will progress, sir.
Mm-hmm.
It will be very difficult for to means remember all the things. Okay,
Okay, okay.
and sir, I just want to give you message that
Mm-hmm.
if you if sir whatever you take that decision that you can revise some concept of previous. Okay,
Okay.
so and sir, there is a session. I think it's Sanjeev also there.
Mm-hmm.
Session with the actual Digvijay sir.
Mm-hmm.
So I think at morning 11:45 session is there.
Yes, yes.
So on that session, sir, everybody asks that what kind of question will be actually asked in the exam because sir, it is quite difficult for us to if some exam will be conducted in MCQ level,
Okay.
and SAT told that you can consult with the you and other peoples because SAT is run this course for last 8 years,
Mm-hmm.
and SAT told that I am not responsible to make any question. So
Mm-hmm.
all the teaching assistants, those who are associated with you, you
Mm-hmm.
just ask them to revise some concepts,
Mm-hmm.
and based on actually, sir told that you three people are the maker, question maker. I think.
No, I'm not making any question paper. So I think someone whosoever is making your assignments will make the question paper. And I don't know who is that person.
Okay, sir, no issue. Sir, just it is my request that I just want to confirm that is you are taking the class today. And second thing is that whatever you discuss that you can discuss some important topics.
Hmm.
You
Yeah, sure.
you discuss this sir first, sir, then you can move to the week 10. Okay, sir.
Okay, okay. I will just cover from I think from lecture third, we will just touch upon the topics. Okay.
Okay, sir. Lecture third. Okay, sir. Okay.
Okay, so let's revise whatever we have discussed from the lecture third. Okay, let's go through that.
Okay, sir. Okay.
So I think from the concept of mobility, you must be knowing that there is how easily the electrons or holes can move through a semiconductor. That is the mobility. Okay, so the movement of electrons when the electric field is not applied, there is always a movement of electrons. That is the random movement of the electrons. Okay, and with that, when you apply the electric field, there will be the okay. Wait. When you apply the electric field uh, with collisions, there will be a net movement of the either electron or the hole uh, to the direction of the electric field. Okay, that in the direction of the electric field is the movement of hole, but in the opposite direction of the electric field is the uh, movement of the electron. Just give me 1 minute. Someone. Okay. Okay. So that is the concept of mobility, and this is given by uh, okay. And when you apply the electric field, this is some given by this is the electric field, and dp by dt, this is the current due to the electric field, and which is given by number of electrons into the charge into the electric field that you have applied. Okay, so
Okay, sir.
I think we should not go that much into deep, right? These are the just okay. This is kind of a bit important.
So,
That
sir,
is the scat.
del Px by dt will be the
This
current.
this is the dp by dt is the with the field. I think this is the current.
Current due to, sir, applied electric
Holes.
field.
Current due to applied electric field.
Okay, sir. Okay.
Yeah, or also, I also forgot these terminologies because everywhere these terminologies are a bit different. You can just check once, okay? I is equal to
Okay, sir.
N E A V D. V D is equal to uh, mu by this. Okay. This is the thing is now let us come on the scattering. So there because the mobility depends on the scattering. Okay, and how does that depends with the temperature increase or decrease? How does the scattering? How does the scattering happens inside a semiconductor? Okay, so if there is an electron or hole moving inside a semiconductor, because inside a semiconductor there are some atoms are also there, right? Inside because of the atoms, this hole or electron is moving, so it will feel a bit difficult to go through these because of the yes. Okay, so because of the lattice scattering. So and if you increase the temperature, then what will happen is there will two things will happen. One is the movement or the motion of these atoms at their position, they will vibrate. Okay, and another thing is when you increase the temperature, the velocity of this electron or hole will also increase due to that. Okay, when you increase the
Sir,
temperature
one more time, sir.
huh, so
One more time, sir. Repeat, sir. When you increase the temperature.
okay, when you increase the temperature, two things happen. One is these atoms are always vibrating at any temperature, right? When you increase the temperature, that motion of that vibration will increase. Okay, that amplitude of vibration will increase, right? And due to that scattering,
Okay, sir.
if something is happening, if something is going through the through this lattice, so it will feel more difficulty at the higher if you increase the temperature. Okay. And there are another thing, there are some in this lattice, when you dope the semiconductor, there are some impurities. When you dope the semiconductor, these are ions. Positively and negatively charged ions are always there. Okay. Someone is joining. So, hmm, so they will feel some force, attractive or repulsive forces will be there, right?
Yes, sir.
Due to attractive and repulsive forces will be there because of the ion impurities. So whenever, and this is the field, like let us say this is the atom, and this is the, you can just say a field up to which the effect is there. Okay. And when you an electron is moving, let us say this electron is moving at this position. Okay, this electron is moving in this direction, and it will have some certain velocity, and the effect of force or attractive or repulsive force is very less at this, the green one that you can see, right? Because it is far away. So the scattering, it will feel at least scattered. But if there is some, uh, let us say this red one, it is going from this point, it was going, but it will feel a bit, okay, at this point, it will feel a bit uh, attractive forces because it is going in the proximity of the electric field of that is generated by this atom, right? The nucleus. Okay, this electron. So it would be going this direction, but it may go in this direction. It may take a U-turn and it may go this direction. Okay, that depends on the temperature, whether it will go in this direction or it will take this one. Okay, if the temperature is high, if the temperature is high, the velocity of this electron will be more, so it will go, it will take, it will feel a less effect of that because it has a high velocity. Okay, it will go in this direction. But if the velocity temperature is low, velocity is low, it will go in this direction. Got the point?
Sir, you mean that if the temperature is low or velocity is low,
Yes.
red one will follow the parabolic path.
Not, we can say it will follow this kind of path. It will deflect more. The main purpose
All
is the
right, not
deflection.
it,
Main purpose is the
yes,
deflection.
yes, reflect more.
Yes. If the velocity is more,
But sir,
the deflection will be less.
so sir, if the velocity is more,
Mhm.
then it can follow the outermost path, outermost.
Yeah, it can go straight as well.
Okay,
Okay.
okay, okay, sir.
Yeah, but there will be, if it is going in with the close proximity, it will definitely feel some force, so it will go like this. Okay, so that is the scattering by the ionized impurities and vibrating atoms when they these are the lattice atoms. Okay, these lattice atoms are vibrating at their own position. Okay, so when something is it will go, so it they will collide with these atoms. Okay, so it will go this thing. So that hinders the mobility. Okay,
Okay,
so
sir.
okay, this is the formula that we have derived, and you can check this one. This is the mobility formula. Okay, and this is the direct relation. Mu is equal to, or if you V is equal to mu E. E is the electric field, mu is the mobility, and V is the velocity. Okay, drift velocity of the electron. Okay, or hole, and mu is the mobility associated with that you can calculate. Okay, but up to certain electric field, as the electric field, it will be constant, it will follow this one. Okay, it will follow this up to certain, but after that it will saturate. Okay, that is because of the scattering. Okay,
Sir,
that
F is the force, na?
huh? E. This is E.
F,
F where
okay,
this
E.
F
Apply
this F
electric
is
field.
the field. Okay,
Okay.
this is not force. This is
Applied
the
electric
field.
field.
Hmm?
Applied electric field.
Yes, that is the applied electric field
And,
across this.
and,
Okay, across
and
this
V is the
semiconductor.
velocity.
V is the velocity, that is the drift velocity that an electron will move after applying the electric field. Okay,
And sir, here the proof is V equal to A lambda,
V is equal to
A tau, A tau, A tau, A tau.
A
Tau
tau.
is a time constant.
Yes,
Time,
time constant. That is the time taken during in between the average time in between two collisions. Okay.
okay. Sir,
Yes.
how A can be write Q by M star?
Okay. Qt by m star. Q tau by m star. That this is the relation that came. V is directly proportional to E. That is V is equal to mu E. Okay, V is equal to mu into E, or here I have written F field, and from this relation we can see that this is the mu Q tau by M star. Okay, this one.
Okay, okay, sir. Okay, okay, sir.
Okay.
Okay, sir.
Hmm. And now and whole mobility will be lesser because M for that M star is higher for the holes. That's why. Okay.
And sir, one more time.
Uh-huh.
Sir, whatever you told that up to certain electric field, the
Mhm.
mobility will be constantly increased. After that, it can be
It will saturate.
decreased. Huh?
It will saturate. Huh.
Saturated.
Mhm.
Okay. So that this value is fixed 7 into the 4.
Yeah, it is almost fixed. Not fixed for different semiconductors. It should be different, I guess, because drift. This is the okay. Let me think about that because, or we can say this is the maximum velocity this can achieve, and uh, it is almost fixed around.
I think that it is material dependent, sir.
That very less in like not that much, very less. It is almost at that level only
Okay.
because
And
if you
sir,
that is
why the graph?
this comes from the kinetic energy. So you cannot go beyond some amount of the maximum velocity. You cannot go from actually we are not going that much deeper. If you read about the kinetic theory of the gases, in that one this will come. So it is
Okay.
actually out of scope of this course.
No issue, no issue. Sorry, sir.
Yeah. Okay, no problem, no problem.
And one more thing, sir. Sir, you told that the graph for starting from 10 to the power 3 will be because, why, sir? Because the temperature require
No, no,
to
no. For
start
lower, for lower electric fields, it will for
not
lower electric fields, it will go lower. The velocity will be
lower
lower.
electricity.
Yeah, it is the electric field. It is just to show that it is saturating. We have started this. So that velocity will saturate because of the scattering of the electrons and
Okay.
holes that we have discussed in this previous, and we will discuss in the next one as well. Two types of scattering: impurity scattering and lattice scattering, that we will see. Okay, can you give me just
Okay, sir.
2 minutes? I'll be coming.
Yes, sir. Yes.
Okay, just give me 2 minutes. Hello.
Yes, sir.
Now, uh, now if you have further doubts, you can ask or we can proceed. Okay. So effect of temperature on temperature and doping concentration. Okay, this we will see once. So effect of temperature will be that is on the mobility. Okay, when you increase the temperature, there will be lattice vibrations. Okay, and there will be some uh, lattice vibrations, and that velocity of the electron or the hole, that is the charge carrier, will increase with the temperature. Okay,
Yes, sir.
so so okay. Hmm. Impurity scattering. So whatever this is given, so this is the mobility that is given. Okay, this is the
Okay, sir.
mobility mu, which is given, that is associated with any electron or hole. Okay, with impurity scattering, it is shown that with impurity scattering, this is the temperature T. Okay, so if you increase the temperature, the impurity scattering will decrease. If you, okay, there are two things. One is the, let us first divide it into two parts. One is the impurity scattering. Impurity scattering is because of the ions, and because of the ions which are in the in your
Doping,
semiconductor.
doping.
Okay, due to the doping in your semiconductor. So the impurity scattering will decrease with the temperature, because it will the electron or hole will spend less time in the proximity of the electric field of the ion. Okay, so the impurity scattering will be less, so the mobility will increase with the temperature, with increasing the temperature. If you increase at lower temperatures, okay, at lower temperatures, at higher temperatures, what happens is lattice scattering starts dominating. Okay,
Sir,
scattering.
one more time, sir. One more time.
Okay, so there is one impurity scattering and one lattice scattering. Let us look into the impurity scattering first. That is this.
Okay.
Okay, so in during at lower temperatures, the impurity scattering is more, because at lower temperatures there is the electric field, or the influence of electric field will always be there at either at lower temperatures or higher temperature. It will always be there. Okay, so the
Okay, sir.
lattice vibrations are not there at lower temperatures. Okay, so the dominating part is due to the impurity scattering. Okay,
Okay, sir.
mobility will decrease at the will decrease with lowering the temperature, because this impurity scattering, this will dominate, will increase. Okay.
So, sir, due to impurity scattering,
Mm-hmm.
your uh, mobility is decreased.
Yes, mobility will decrease with decreasing temperature.
But, sir, here so it will show that increasing at lower temperature.
Mobility will decrease. Okay,
But, sir, the graph will show that it will be increasing in nature, na?
no.
You put
Okay,
the you
this side temperature is decreasing. This mobility is decreasing. Okay, with increasing temperature, mobility will increase at
okay,
lower
okay, okay. This is
temperatures.
okay, 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 okay.
Okay, so at higher temperatures, lattice scattering will dominate, and mobility starts again decreasing with increasing temperature. Okay.
Okay, so it will be
Mhm.
maximum at middle part of the temperature.
Yeah, at somewhere like say 100, in between 100 to 100 degrees. Okay,
Okay, sir. So, sir,
100,
at
not
higher
100 to
temperature,
100 degrees, 100 to 100 Kelvin.
Kelvin,
Yeah.
Kelvin. Okay.
Mhm. Yes.
So, sir, at higher temperature, lattice scattering will be highly acceptable, and at lower temperature, impurity scattering will be highly acceptable.
Yes. It will be
Okay,
there.
sir.
Yeah. But both will be there, but the effect of the impurity scattering will be more, will dominate at lower temperatures, and lattice scattering will dominate at higher temperatures. Okay.
Okay, sir.
Yeah. So another thing is the is the doping concentration. If you dope the semiconductor, what you are increasing in the is the impurities, right?
Yes.
If you are increasing the impurities, you are increasing the scattering. Okay, this is the doping concentration. Okay, this is the doping concentration. If you are increasing the doping concentration, that then what happens? You are increasing this lattice scattering, and your mobility will decrease. Okay, it will
So, sir,
start dominating again at room temperatures as well. Yes.
sir, but I heard that if we increase doping,
Hmm.
it can increase the uh, conductivity.
Yeah, you can increase the conductivity, but mobility and conductivity are different things.
Sir, if conductivity is increased, sir,
Hmm.
electron can get easy path to move through the device.
Yeah, if you
No,
conduct,
actually, sir, this is whole mobility, sir.
this is mobility, not the conductivity. Conductivity and mobility both are different things.
But sir, resistance and mobility is there any relation?
Huh?
Resistivity and mobility?
No, no, mobility, resistivity or conductivity, you can say they are reciprocal to each other. Okay, mobility,
No, that I know that.
your conductance of the material depends on the mobility.
Okay, okay, sir. Okay,
Okay, because that your conductance depends on the mobility and the carrier concentration. Okay, so
okay,
your conductivity or conductance is increasing because of the carrier concentration is increasing when you are doping the doping. Okay, so
okay,
if you see, there are two things. One is the mobility and one is the conductance. Okay, your
okay,
conduct with doping, if you let us say D is the doping, if you are increasing the doping, your mobility will decrease after certain doping. Mobility will decrease. Okay, if your D is increasing, you are increasing ultimately N charge, number of charge carriers. Okay, and you are increasing the conductivity. Okay,
okay,
I
sir.
actually mu is I is equal to N E A V, and Vd is equal to mu into E, and J, the N into E into mu. Okay, your this conductance C is equal to N into E into mu. Okay, and your conductance C, if you can go through the
Okay,
formula as well, so that is equal to, this conductance is equal to conduct, not the conductivity. Conductivity depends on the uh, on uh, on your area as well. Okay, this conductance is divided by area. Okay, so
okay,
that is your conductance is N. N is the charge carrier concentration, E is the charge, and mobility. It depends on these three things, and mobility is the material property. Okay, it's, and it depends, it changes with the doping concentration, with the temperatures and all these things. Okay, and your conductivity depends on mobility and the charge carrier concentration. If you dope the semiconductor, you are doping, you are increasing the charge carriers, not the mobility. Okay.
repeat one time. What last sentence, sir? If
Okay,
we increase
if you are increasing the doping concentration, you are increasing the number of charge
mobility
carriers.
decrease.
You are increasing the
Yes.
number of charge carriers. Okay, and electrons, either
Okay,
electrons or holes, whether you are doping P type or N type, depending on that, it will be holes or electrons respectively. Okay.
okay. And
And
sir, the graph shows that mobility decrease with the doping concentration.
with the doping concentration, yes, that is the mu mobility,
Okay,
not the conductance, and your conductance will increase with the doping.
okay,
Okay.
sir. Okay.
Yeah.
Okay, sir.
So
Sir, please go to the last slide. One minute.
yes, yes.
Last slide.
Previous
Um,
this one,
no. That's one, sir.
this one.
Okay, okay.
Hmm. Okay. So these are the graphs that I have taken from the book. So with the impurity concentration, these are the like whole mobility, and that is the this electron mobility. The blue one is the electron mobility, and black one is the whole mobility. With increasing the concentration, they decrease. Okay, they decrease. This is
So why the three graphs, sir? For different material.
for different
Okay,
materials. So this is for
okay.
silicon, this is germanium, this is gallium arsenide.
So, sir, it is better to use direct band gap gas is stored because
Which
it will be increase the mobility.
why?
Because the gallium arsenide has a high value of mobility, sir.
I don't think that depends on the on your band gap. If whether it is direct or indirect.
No, sir. I just want to ask you that if the impurity concentration is increased
Mm-hmm.
for three different material, gallium arsenide will be
Mm-hmm.
high mobility there.
Yes, that can be. There could be some different reasons, and gallium arsenide. That depends on the size of the of your these atoms as well. Okay,
Okay.
size of the atoms, and the if you are increasing with doping concern, which doping you are doing. Okay, so I think that can be either increasing the gallium concentration or arsenide concentration in gallium arsenide itself, because this is
Okay.
a
Okay.
3,5
Compound,
semiconductor.
compound
Okay,
semiconductor.
so
Compound semiconductor.
how can you dope the 3,5 semiconductor is at undoped it is 50-50. Okay, if you increase the three concentration, that gallium concentration, if you increase 60% and this is 40%, then it will be a p-type doped. Okay, if
Yes,
you
yes.
huh,
And
so
reverse will be entitled.
huh, so maybe because of that, because the same thing is there, so because of that it is showing lesser, but there is germanium as well, that need to see. I think
Okay, sir.
that also depends on the size of the atom that you have. Okay, that size of the atom is germanium is bigger than the silicon. So bigger the size, I think already lattice parameters are far apart. Electron can move easily through that, and also if you are doping it with other material, so that let us say with the gallium only. Okay, if you are doping it with gallium, so that has a smaller size, so the lattice parameter, I think that depends on the lattice parameters as well, so why
Sir,
this decrement is lesser.
sir, as per you, sir, there are several parameters are there which can affect the mobility. So, if the size of the
Mhm.
gallium is large, there
Mhm.
will be high chances of collision. So because
uh,
that is considered to decrease.
uh, no, I don't think so. There can be some other things, because in gallium the charge, there is one more effect, the charge shielding. Have you heard about that? So for gallium, if you are going in the same periodic table from top to bottom, the charge shielding by the electrons in the shell is more. Okay, so if you are going from top to bottom, like silicon was there, germanium comes below that, and
Hmm.
uh,
Carbon.
uh, okay, carbon is the above. Uh,
Yes,
uh,
yes.
so what I was saying is, for gallium, if you are doping it with gallium, uh, this. This depends on the actually that is a bit chemistry. If you want me, I can discuss that in detail as well.
No,
But
no, no, sir. No, sir. Don't,
it
don't
is not
require.
required for
It's not
this one. That's
written.
why. But that
Okay, sir.
also depend that what I was saying is the decrement is that could be because of that. That could be a reason, but I'm not sure about that. But what I'm feeling is that is the reason is the like if you go are going from top to bottom, your uh, your this lattice parameters are increasing. That is definitely. Okay, lattice parameters are increasing, and
Okay, sir.
electrons and holes are less kind of sort of scattered
Separated.
because of the lattice scattering. Okay, and your total mobility mu is is the geometric mean of 1 by mu total is equal to 1 by mu scattering by a lattice scattering plus 1 by mu of this scattering. Okay, that must be given here. Phonon scattering and ion impurities scattering. Okay, so
Okay,
this
sir.
is the total. Okay. So both are there. Both are there. So in this one, there may be less that lattice scattering because of the far apart. These atoms are far apart, right? In the lattice. Okay, but it is not
Okay,
required.
sir. So,
This these type of questions, I don't think they will ask. Okay,
okay,
but
okay, sir. Okay, sir.
what you need to know is this mu total is 1 by mu lattice scattering and ionic scattering that is given here, this one. Okay, you need to know that.
Okay, sir.
Okay, and this graph is important. Okay, effect of temperature on the mobility. Okay, this is the mobility, and effect of doping concentration on mobility. This is also important. Okay,
Okay, sir.
yeah. So this is not required that much, but what you need to know is what you the takeaway is. So at equilibrium, at equilibrium, uh, so whatever happens, the Fermi level is always constant. Okay, this is the takeaway
Okay, sir.
from this slide. So when you join two materials, material one and material two, okay. So at equilibrium, when it attains the equilibrium in some time, so the Fermi level will be constant. Okay. So when you apply the field, there will be there are two things. Just you can note it down that there are two things. When you apply the field, when there is a current in a semiconductor. Okay, so this is the okay. I'll take a new slide. So this is conduction band, this is valency band, and this is the Fermi level. EF, EC, EV. Okay, this is when when I is equal to 0. I is the current. Okay, and electric field. Uh, I uh, uh, I am denoting with this. This is electric field. Okay, this type of E, okay, is 0. So
Okay, sir.
so electric field is 0, then what happens is the bands will be flat. Okay, elect this conduction band and valency band will be flat. Okay, so this is the and
Okay, sir.
I is equal to 0. So that defines the current is 0. Okay, current is 0, that means this Fermi level is constant. Okay, this is Fermi level is constant. Got the point?
Okay, sir.
So
Yes, sir.
whenever this current is Fermi level is flat, then it is the this is the equilibrium condition. Equilibrium. Okay.
Okay, sir.
Hmm. Or when there is gradient in the conduction band and valency band. This is the EC, this is EV. There is some gradient in the conduction band and valency band. Okay, so
Okay.
if the Fermi level is constant, this is the Fermi level, EF is constant, then current is zero. Okay, but electric field E, in this case E is not equal to zero, but current is zero. Okay, because Fermi level is flat. Okay,
So Fermi is flat, then I equal to zero, but electric field is not zero.
electric field is not zero because this conduction band and valency band are not flat.
Okay, sir.
Okay, this is also an equilibrium condition. Okay,
Okay, sir.
so whenever there is any gradient in the Fermi level, let us say this is the Fermi level, this. Okay, this is the Fermi
Okay.
level. So then I is not equal to zero in this case. I is not equal to zero. Current is flow. Okay,
Current is, sir.
current is flowing in the semiconductor.
So I is not zero, E is also not zero.
E is all E. Okay, whenever you are looking at the electric field, then go to the conduction band and valency band. When you are looking at the current, go to the electric this Fermi level.
RV level. RV level.
Yes. Okay.
Okay, sir.
Yes. So if
So, sir,
there is,
when Fer- sorry, sir, for interruption.
hmm, hmm,
When the when the Fermi level is slanted,
hmm.
we say that the electric field is not zero.
No, Fermi level is
No, no,
hmm,
I is not zero.
I is not zero. Yes.
But to see the electric field, we have to see the band is flat or not.
Yes. Exactly.
Okay, sir. Okay.
Okay.
Okay, sir.
Hmm.
Okay.
So that was the takeaway from this one. Okay. So this is shown that dEF by dx is equal to 0 for when there is no current flowing. Okay.
Okay.
Hmm. So this is the excess carrier absorption. This is not required. Luminescence, photoluminescence. These are gone things. Einstein relation, just remember that dn by mu n is equal to kBT by q. Okay, and this is also equal to
Even,
dp by mu p. Okay, this is the Einstein relation.
sir,
Mm-hmm.
can you move to the slide? Just you say that when the equilibrium condition dfx by dfx
That
by
dEF
dx
by dx is equal to 0. That means there is no gradient in the Fermi level.
Fermi level.
Fermi level is flat. That's why dEF by dx is 0. There is no gradient in the Fermi level.
Fermi level. Okay. dx. Okay, sir. And Einstein relation, sir?
Hmm.
Einstein relation?
Okay, just give me 1 minute. Einstein relation is dp by mu p or dn by mu n is equal to kt by q. Okay. And there is one question, I think, in assignment fourth on this one.
Sir, proof is not required, sir.
Proof is not required.
Okay, okay, okay.
Or although I have shared the slides, you can go through them as well. Okay.
Sir, you can share your, you have, I think you have done the whole course, 12-week course, sir. Because I think 230 slides are there.
In this one, yeah, in this one, 230 slides are there, but I have
Yes.
segregated them.
Okay,
So
okay,
with I have segregated them with the lectures. Okay. So
okay, sir.
one, two,
Okay,
three, and all. I have shared all actually. I think I haven't shared all, but with the lectures I am sharing.
okay, sir. Okay.
Okay.
No, sir. Actually, I just, with the permission of father, I just want to give you the, if you possible that you can share this with the, when all slide, if you share, sir,
Mm-hmm.
and if you, actually, I have mailed you today at
Yes.
noon, sir.
Mm-hmm.
So actually, if you give me the all slides, sir, I
Mm-hmm.
can means I can take the revise one more time,
Yeah,
and I
you
just ask you these slides are I have facing difficult, sir. It is the easiest way to study, sir, in a short time, sir.
actually I don't think you will understand these things. Will you
Yes,
understand
yes, yes.
what is there?
No, no, no,
You
no, no,
won't
no, sir,
understand,
no.
right? You
Okay,
won't
okay, okay,
understand
okay,
that.
sir. Okay.
Okay. So, and that will come with the whenever you are attending the lecture
No,
or
no, sir.
whenever.
Okay.
Okay. So, so that is the recombination and generation is given. I think this one. So there are certain recombination. This is not required for this course. I have included these, but I will tell you about the recombination and generation in this one. Maybe this is good, sort of. Okay. So, whenever you, there is a, okay, this one is fine. Hmm. In intrinsic semiconductor, this is the, okay, this is the band gap. Okay. This is the band gap. And at any temperature T, there are some electrons from the conduction from the valency band. They are jumping in the conduction band, and at the same time there are some electrons that they are coming back from the conduction band to the valency band. Okay, this is the
Okay.
carrier generation. This is the generation when there is some electron is jumping from valency band to the conduction band. At that time there is one electron. After this process there is electron and there is hole left. So this is the generation of the electron hole pair. Okay, so at certain temperature, at any temperature, this process is always going on. Okay, so the generation and at the same time, there is recombination is also going on at any temperature. Okay, so this is equal at equilibrium. So whenever you pick a semiconductor, that semiconductor is in equilibrium at that temperature. So this generation rate G is equal to recombination rate R.
R.
Okay, at equilibrium, this generation rate is equal to the recombination rate. Okay, so
Okay.
there are some, no, we are not discussing the traps here. So if you, anyways, you take the semiconductor in and some in equilibrium state. Okay, at equilibrium what happens is this Pn is equal to Ni square.
Mass
Okay,
action loss, sir.
this, yeah, this will hold always whenever that semiconductor is in equilibrium. If the semiconductor is not in equilibrium, uh, or how does a semiconductor comes a non-equilibrium state? Whenever you shine a light, okay, when you apply a voltage, sudden voltages and all sudden application of the light, so at that time it goes and a non-equilibrium state, right?
Yes, sir.
So this Pn is not equal to Ni square at that point time. Okay, so this when you apply some light, something, so electrons and holes are generated, right? If you shine some light, okay, shine some light in a semiconductor, some holes will be generated. So delta n number of electrons are generated and delta p number of holes are generated at that time. Okay, so
Okay, sir.
huh,
Yes, sir. Yes, sir. Delta n
so
number of electron, delta p number of holes are there.
so this delta n is equal to delta p because these always generate in a pair. Okay.
Okay, okay, sir.
So this delta number of whenever you shine a light, there will be equal amount of generation. Okay. So
Okay, okay.
if you are increasing, so it was P and N. So now let us say P naught and N naught at equilibrium. So now it is P and N after you shining the light. So P is equal to P naught plus delta P. And n naught n is equal to n naught plus delta n, right?
Yes, sir.
Okay, so so
Sir,
when you Mhm.
this P not will be previously there, and after the light shine, the delta P will be extra amount of carrier produced.
Yes,
So
these are
now PL will be,
so these are the extra excess carriers delta n and delta p, right? These are the
okay,
excess
sir.
carriers. So if now Pn is greater than Ni square, right?
Yes, sir.
So this will always try to go back in the uh, equilibrium state, right?
Okay.
So it will try to go
Yes,
back in the equilibrium state. So it these whatever extra delta n and delta p are there, so they will try to recombine. Okay, if delta
okay,
n
sir.
they will try to recombine. Okay, or if Pn, if any in any case Pn is less than Ni square, then they will it will generate the carriers.
Sir, when sir P into N less than Ni square sir happen
So
after recombination.
this, okay, Pn is greater than Ni square, then it will recombine. Recombination will happen.
Okay.
Okay, if Pn is less than Ni square, then generation will happen.
Sir, how the condition is sir less than Ni square?
This is the condition. Okay, there will be, and
Oh,
I think there is one. I have added the formula as well for that. Not in this one. Mm, Maybe in the later slides I have added the formula as well. Here, not here. This one. This is the total net recombination,
okay,
net
sir.
generation
Actually,
or recombination. Mm-hmm.
I want to know the condition.
Mm-hmm.
Actually, I just want to know the condition where Pn less than Ni square. When it is occurred, sir.
When Pn is less than Ni square, this itself is the condition. Okay, when is it is there now?
Actually,
Okay.
then after recombination,
Mm-hmm.
if the if the generate amount is means the generate amount is less than recombined amount, then I think, sir, because of temperature, I think because temperature
No.
there will be
Okay.
extra
Okay.
recombined.
Okay. You are asking me some kind of example where it happens, right?
Ah, yes, yes, sir.
Okay. So, hmm, uh, there is one thing we have studied MOSCAP, right?
Yes, sir. Yes, sir. Inversion.
MOSCAP we have studied in MOSCAP whenever uh, I need to go to that slide. Okay, you are applying some field. huh. At that time, you are in MOSCAP, there were some characteristics, CV characteristics. You remember that these
Yes, sir.
things,
Three regions are there, sir. Three regions.
right?
Accumulation, inversion, and depletion.
Huh. So this is the low frequency uh, one, and this is the high frequency. You are measuring
Yes,
the
sir. Yes,
CV.
yes, sir. I know that. I know that, sir.
You remember? So
Sir, and sir, one condition is that if the frequency means medium, then it will be
mhm,
straight.
yeah. So this is happening because your generation rate is not enough.
Okay.
Okay, that is why it was going below, because at in that case Pn is less than Ni square.
Okay.
Okay,
Okay, sir.
at this junction, and this happens here. So uh, it is not holding with that frequency. That generation rate is not that faster as your frequency.
Okay, sir. Okay.
Okay, this happens in that case. So I think if you remember, and we discussed that thing, ki,
Yes, sir. Yes, sir.
this MOSCAP. Okay, but if you
Yes,
just
sir.
go back and read that thing, but that happens because of the generation of the charge carriers at the at in this depletion region. Okay, charge carriers are getting generated at the depletion region. Okay, because in that case Pn is less than Ni square, and if this is the case, then charge carriers are generated. Okay,
Okay, sir. Okay, sir.
and that
Thank you, sir.
happens because of the high frequency.
Okay, sir.
Okay. Mm. And no, this is going for the high frequency and this is going for the low frequency. In both the cases, charge carriers are generated. But this is our generation rate cannot follow the frequency because the frequency is very high. The generation rate is slower than the frequency. Okay. So, do you understand the frequency, right? If the higher the frequency, the vibration of the atom, you can say if it is
More.
vibrating 60 at 60 hertz, that means in 1 second it goes
60 times.
60 times it completes the
Yes, sir.
revolution.
Yes, sir.
Okay, and if you are applying a voltage at some frequency, let us say 10 kilohertz or 1 megahertz, 1 megahertz is too much. That is like 10 raised to power 6 times in 1 second. Okay, your
Yes.
generation rate is, let us say, you can generate one in the time range of 10, this is the 10 raised to power 6, that means 10 raised to power minus 6 second, right? That is the hertz,
Yes, sir.
one revolution. Okay,
Yes,
so
sir.
if you going to 100 megahertz, that means 10 raised to power minus 8 seconds. Your generation rate,
Sir.
your generation rate, that the time it takes to generate the electron and hole pair, that is lesser than that. Okay, so let us say that is 10 raised to power minus 7. Okay, 10 raised to power minus second, 8 to 7 seconds it takes to generate the electron hole pair. But in 10 raised to power minus 8 seconds, it already changes the polarity. Okay, can you understand that thing?
Yes, sir.
So, but it cannot.
Sir, one more time, sir. I cannot relate the topic.
Mhm.
One more time, sir. 10 to the power minus 8 means sir, 100 megahertz.
Yes, the 10 raised to minus 8 is the 100 megahertz. That is the like one revolution it completes in 10 raised to power minus 8 seconds.
Okay.
Okay, whatever the frequency it is, it's 1 megahertz, 100 megahertz only, right? Okay, but your generation rate is like 10 raised to power, it generates the electron and hole pair in that regime. It takes 10 raised to power minus 7 seconds itself. So it won't be able to generate as faster as your polarity of your voltage is changing. So this is your time, and this is the polarity. It is changing positive and negative. It is changing in the range of 10 raised to power minus 8. Okay. In the
Yes, sir.
because this is the time, it is changing in the 10 raised to power minus 8 second. This is completing one revolution. That means 0.5 into 10 raised to power minus 8 seconds. It will be positive, and then it will go negative, again positive, negative, positive, negative. So it is changing the polarity. So if we are going in that generation regime, it will at this point, if we are going because we wanted to get the electrons and holes, right? If we are applying some,
Yes, sir.
so if it is, we have applied that frequency here. So positive, negative. Got the point? So it is changing the concentration at this point because of the changing in the polarity of a small signal. I don't know if you are because we have discussed this thing in detail at that time as well. So, would you like me to go more into more detail so I can take a new slide and make you understand that point as well. If you want me, I can explain that in detail.
Yes, sir.
You want?
Yes,
Okay,
sir.
okay, okay.
Sir, actually, sir,
Mm-hmm,
sir,
mm-hmm,
whatever you want to tell that,
mm-hmm.
if the timing, if the
No,
applied frequency is more than generation rate,
huh,
if the if the applied frequency is more than generation rate,
huh.
then there will be a PN less than Ni square.
No, it doesn't mean that. It means the graph will be in that regime, in this regime, that CV graph.
Okay, okay, okay,
Anyways,
okay.
anyways, whenever you are applying the field, it is always generating. Whether the frequency is low or high, it is always generating.
Okay,
Okay,
okay.
it is always generating. So, uh, in another example, I can show you. Okay, let us say your this is your semiconductor. Okay, that you have doped the semiconductor 10 raised to power 18 centimeter
Okay.
cubic centimeter per cubic centimeter. Okay, 10 raised to power
Okay, sir.
17 or 18. So if you see, this is the n type n type. Okay, so electron concentration is 10 raised to power 18, and hole concentration is will be equal to 10 raised to power 2 per centimeter cube, right?
Okay.
Got the point? So let us
Yes,
say
sir.
the thickness of not, let's not go beyond 10 raised to power 15. 10 raised to power, let us be here only, 10 raised to power 15. In that case, P will be 10 raised to power 5, right?
The 10 to the power 15. How much? What is that?
10 raised to power 15 is the dopant concentration or the concentration, carrier
Use the
concentration,
10.
N type.
Use the
This
10 to the power 18, sir.
actually I have changed. How much concentration do you want to dope this semiconductor? Let us say this
10,
is the N
10,
type.
10 to the 18.
10 raised to power 18. Okay. This is 10 raised to power 18. So then according to that, how much will be minority carrier concentration?
10 to the power 2, sir.
10 raised to power 2.
10 square.
Okay. 10 raised to power 2. So this is the per centimeter cube. Okay.
Yes, sir.
Let us say this is the 100 micron thick, 100 micrometer thick wafer,
100 10 to the power 6.
100 micrometer. Okay,
100 10 to the power 6.
100 into 10 raised to power minus 6
Minus
meter.
6.
ठीक है?
Yes,
Let
sir.
us go in the centimeter, 10 raised to power minus 4
minus 4.
centimeter. Okay,
Okay,
so
sir.
and the width and the this breadth of the device is, let us say, 100 micron cross 100 micron.
Okay.
Okay, that I have taken too much still. Okay, this is 100 cross 100 micrometer. What is the area? 100 into 10 raised to power minus 4 into 100 into 10 raised to power minus 4. How much will be the area?
100 into minus 8.
100 into, no, that will be 100. Okay, just give me 1 minute.
Okay.
I will.
Okay, sorry, sorry. Sir, okay, 1 into
10
10 to the
raised to
power
power
minus
minus 4.
12.
10 raised to power minus 4 will be the area per centimeter cube.
So 1 into 10 to the minus 12, sir.
So just give me 1 minute. How much? Okay.
1 into 10 to the minus 4. 1 into 10 to the minus 4.
1 into 10 raised to power minus 4 will be the this. Okay. So what will be the volume of, if you see that, if you
Into,
see
sir, into, sir, 100.
1
I have to
into
multiply.
10 raised to power minus 6 uh, centimeter cube will be the volume. Okay. Got this point?
Yes, sir. Yes.
Let us
Yes,
say
sir.
we have made this much area of the this our mouse cap. Okay.
Okay.
So now when you apply a positive voltage here, this is N type, right? So when you are applying a negative, let us say negative, we are applying here, negative at gate. Okay, so it will invert the carrier concentration, right? Whole carrier concentration here,
Yes, sir.
right? So how much whole carrier concentration do we require here? It's 10 raised to
10
power
square.
10 raised to
10
power
to the 2.
18 to invert the channel,
Oh, inverter channel. 10 to the 18, sir.
right? To 10 raised to
But
power 18 we require how much many holes do we have?
10 to
Is
the 2.
10 raised to power 2 per centimeter cube, right?
Yes, sir.
This
Yes.
and how much many holes will be there in this much of volume? This is the in centimeter cube. Just divided it by this one, right? You will have,
Yes.
I think, this much
10
of.
to the minus 8.
So you do not even have even holes. Where are you getting the holes from?
Yes, sir. Yes, sir.
You
I
do
have
not,
not enough.
in whole semiconductor, you do not have that much of holes that you are inverting the channel,
Yes, sir.
right? But
Yes, sir.
you have holes. You definitely have holes after inverting the channel. So where are the holes coming from? They are generated actually, because when you when you apply the field, so at that time Pn is less than Ni square. Okay, this
Exactly. Exactly,
Pn
sir.
is less than Ni square, and at that time, so it will generate the holes, because when you apply a negative voltage, it will deplete, right? It will deplete. It will throw away the electrons, right? When you apply the negative charge.
Yes,
So,
yes, yes, sir. Yes, sir.
so here electron concentration will decrease. This N will decrease here. So what should increase? The hole should increase. How the hole should increase? But we do not have. They will generate at that.
Excellent, sir.
Okay.
I understand, sir.
So this
So, sir,
happens.
so, sir,
So this happens in
so, sir,
every PN junction. Okay,
so, sir,
I took this example of the MOSFET, but this happens in every PN section.
okay, sir. So, sir, can I gist this with whatever I am understand, sir?
Mm-hmm.
Can I gist it whatever I understand?
You can
So,
reach.
sir, if sir, uh, we have a less number of, as we know that the either n-type material will be the majority carrier, minority carrier. So
Mhm.
if I make a n-type material
Mhm.
or p-type substrate, whatever I can say, so
Mhm.
it will be contain 10 to the power 18 amount of per centimeter cube amount of electrons are there, and 10 to the 2 amount of minority carriers are there.
Yes.
So if I apply negative voltage in the
Mhm.
gate,
Mhm.
so we require 10 to the power 18 amount of holes
To
in a
invert the channel.
1 into 10
To
to
invert
invert the
the channel.
channel.
But it is not okay. What I am saying is, I am taking the extreme case. Okay, that I am
Yes,
taking.
yes.
Just apply a small negative voltage, just small voltage. So if I'll just allow me to take new slide. So if it was there, so this was the like semi oxide, and there was a semiconductor, right? And we were
Yes, sir.
bending the band, right? Like this.
Yes, sir.
Remember that. So when you
Yes, sir.
apply
Yes, sir.
the field at this point, the extent of bending that goes, right? You if
Yes,
you
sir.
are
Yes, sir. Yes,
if you are applying
yes,
more
sir.
and more, here is the this is we have taken some I
The
think
metal part, sir.
okay. So here this is the I think P type or N type, whatever this is, we have taken the P type semiconductor.
N type, sir.
It is
P type and sir, inversion will be happening electrons, sir.
so P type I have taken. Okay, so if you are
Yes, sir. Yes.
applying a positive voltage, so it will bend the bend like this. If the extent of bending, this much of bending depends on how much voltage you are applying, right?
Yes, sir. Yes, sir. Yes,
If you
sir.
are applying a small voltage, then the bending will be less, right?
Yes,
So
sir.
if you are applying the more voltage, the bend, so generation will always be there. So when you apply a small, very small voltage, it will generate the carriers.
Okay, sir. Okay.
Okay, it will definitely
Sir,
generate the carriers.
based on that, sir,
Mhm.
there will be sir inversion, or either it will be
Ah,
strong inversion or weak inversion.
that depends on the voltage that you are applying.
Yes, sir. Yes, sir. Okay, sir. Okay, sir.
So got the point, right?
Yes, sir.
Okay. So now there is a diffusion of the charge carriers. Okay. So how why diffusion happens? Diffusion happens because of the gradient of the charge carriers. Concentration gradient is there. Okay. So if you are doping the semiconductor and this is the direction X, this is your semiconductor. Let us say this is the semiconductor and you have doped the semiconductor. You have doped the high doping is this. This is the highest doping. This is the highest doping in this region, and that is that doping graph is like this. Okay, so there will be some because of the concentration gradient, it will the electrons are higher in this region and lower in this region, they will flow in this direction. Okay,
Sir, one more time, sir. I cannot relate, sir.
so electron concentration is high at this in this region, right? This is the
Okay.
concentration graph and low at in this region. So electrons will flow from this region to this region because of the concentration gradient.
Okay.
And the charge as the current associated with that because of the concentration gradient that is given by the diffusion current.
And sir, actually, this graph will be depend upon doping, na?
Yes, this is the doping. Or this can doping or excess charge carrier concentration that doesn't uh, uh, what to say if this is your semiconductor. Okay, let us say this is the semiconductor. Okay, so there are several reasons how the carrier concentration can vary, can be this. Okay, if you are shining the light in this region, okay, in this region you are creating the charge carriers more. So more the here in this region there will be more charge carriers and in this region there will be less number of the charge carriers, right? So the charge carriers will try to move in this region.
Yes, sir.
Okay, so that is also the diffusion because the when you shine the light, here will be the more number of charge carriers and here will be less, so it will they will diffuse from this end to this towards this end.
Okay, sir.
Okay. So,
Okay.
so
The
mhm.
formula you want to remember, sir?
These formula, this is the diffusion current because of the concentration gradient of the electrons, and this is for the holes. This formula you have to remember, and this is the total diffusion current. Okay.
And difference between both these two.
Hmm?
Difference between addition of total.
Yes, total. This is the electron and hole. Okay.
Okay, okay.
Yes. So, and a drift current is due to the electric field, right? When you apply some electric field, this is the application of the electric field, and there are number of holes and electrons are there inside the semiconductor, and E into N into mu N. This is the due to electrons, and this is due to holes. Okay, the drift current due to
Okay.
electrons and holes. This is the total drift current. Got the point? This is the
Yes,
total
sir.
diffusion current. And inside a semiconductor, the total current is because of the drift plus diffusion of electrons and holes both. So total current inside a semiconductor, this is the drift current and this is the diffusion current. Total current inside a semiconductor is the drift plus diffusion.
So
Okay.
total current inside semiconductor drift or diffusion.
Yes. Okay.
Okay.
So this was, and then comes the continuity equation. Have you ever seen?
So we have seen, sir, but
Okay.
if you sir recap, sir, it will be better, sir.
Okay. In continuity equation, let us say this is a piece of semiconductor. This is a piece of semiconductor, and let us say this is a small portion that is divided into dx. Okay, small portion, also small width dx that we have taken here, that is the delta x, we can say. Okay, the current that is going inside at this end and coming out at this j x plus dx distance. Okay, let us say this is at x, this is x plus delta x. Okay, so current entering
Yes,
and
sir.
coming out. Okay, so that will be depends on the on several things. So if you take a piece of semiconductor or anything, any current, so you think, okay, let us take a pipe. You are pushing some water from this side and you are taking water from that side. So that water, whatever amount you have pushed from this side, will you will get the equal amount that will be pushed out this side, right? Let us say you
Yes,
have
sir.
taken, okay, my video, you cannot see me, right? So let us say this is a piece of pipe. So you have pushed some water. Okay, let us say 1 liter of water you have pushed, and you will get 1 liter out of it, right? But
Yes, sir.
in case of semiconductor, whatever you are pushing some current at this end and you are getting some current at this end. So these currents won't be equal because there will be some generation will be there, carrier generation will be there, carrier recombination will be there. Because of these, that carrier so the current won't be the same. Okay, so what we will see is we will look into it, how we can find out that. Okay.
So sir, in semiconductor,
Mm-hmm.
the if I give some input, there will be due to generation recombination, output will be more.
If you if you give I sorry, can you repeat?
Sir, if I in case of semiconductor, if I apply some voltage or current,
Mm-hmm.
the the output will be not the same as the in case of pipe.
Yes, Yes.
due to generation recombination. Due to
Due
generation
to
recombination.
generation recombination. Yes.
Okay, okay.
Okay. So there will be some because some brain boundaries and all, there will be some recombination and all. So you can see this is the uh, change in the carrier concentration in this one. Okay. d of dn by dt is the change in the carrier concentration. Change in the carrier concentration, that is the electron concentration with time in this region, or whatever that we will find the carrier concentration, that is per centimeter cube is it is given. Okay, we will see that. Okay, so uh, uh, should I go through that? Okay, let us come directly on this. The carrier concentration, the change in carrier concentration dn by dt is equal to 1 by q del of jn by dn del x, and plus generation minus recombination. Recombination is del n by del tau, del n by tau. Okay, this is the recombination rate that you can put here, and this Jn you can put here. We are going a bit faster. Okay, okay. So what we have done is we have put this equation Jn in this equation. Okay,
Okay, sir. And
okay.
sir, first we have to perform the derivative.
Uh, uh, yes. So this is the change in carrier concentration in a semiconductor. Okay, this is the change
Okay,
in carrier concentration inside a semiconductor. Got the point?
okay.
Huh. And this
Change in carrier concentration in semiconductor.
in inside a semiconductor, when you when there is a flow for uh, or there is current or not, that doesn't, that we will come on to that point. Okay.
Okay, sir.
There is some diffusion, some drift. So uh, we will segregate both this. This is the because of diffusion, and this is because of drift, right?
Sir, for one type of carrier,
For one type of carrier, N type we are taking.
uh,
Okay,
in type. Okay.
N type we are taking, and we have put this in this equation J and X. Okay.
Yes, sir.
So what we can
In
see, J and X, this depends on X. So this carrier concentration, that N uh, is okay. If you have seen in the previous slide, so what we were seeing is there diffusion is because of the carrier concentration. This is N.
yes, sir. Yes,
So this is the NX, right? NX, this graph. So you can put that equation in this one, okay. Just that diffusion, so it will give you the diffusion current, right? And if there
yes,
is
sir.
some application of electric field as well that you can apply here, and if you put this equation, this Jn in here, what you will get is you will get this equation. Okay, just what I have done is I have put this equation. Okay, so n is converted into, if there is some excess carrier. Okay, so this is the excess carrier n plus delta n naught plus delta n. This n. Okay, whatever the excess carriers are there, n naught plus delta n. Delta n is the excess carrier, right? So these
Yes,
excess,
sir.
whenever there is recombination and what changes is the excess carrier. Okay, whatever changes with time, anything that changes the excess carriers only, not so this will try to go, whatever excess carrier, this they will try to diminish. Okay, so they will try to go towards the equilibrium. So this is the equilibrium carrier concentration, this is the excess carrier concentration, and this excess carrier concentration will decay with the time, and how that will decay, that we are going to find out. Okay,
Okay, sir.
so it is a bit difficult. Well, if you go through the book, you will get more insight into it. Okay, so
Okay, sir.
this is the equation that we got after after solving these two. Okay, this is the drift plus diffusion, and we have we got this from the continuity equation. This is the continuity equation we got, and then we put this in this one. This is the like derived continuity equation after putting the drift and diffusion components. Okay, so
One minute, sir. 1 minute.
hmm,
This is a derived quantification.
this what no, we have derived sort of derived this equation. So so let us see the components of each components of the equation. Okay, then you will
No,
get
sir. I understand, sir. I understand. Sir,
uh,
first part will be the diffusion. Second part will be drip. Then generation and recombination.
this is the diffusion, this is the
This
drift,
is drip. This
this
is
is
generation
generation,
recombination.
this is the recombination. Okay, and this is the change in the carrier concentration with the time.
Time.
Okay, now there
Sir,
are two things
we have to
come.
find out the gradient.
Now there are
We have
two,
to
three
find the
things.
curvature, sir. Curvature.
Hmm?
I think in del square n and ds square, we have to find the curvature of the hyperbolic solution.
No, this is an example of something. So I will tell you what is this thing. Okay, what is this thing?
Okay.
Okay, so let us say this is a piece of semiconductor. Okay, and somehow you have shine a light. Okay, at this end. Okay, and you keep shining the light at this end. Okay, it will go in
Okay.
some steady state. Okay, so
Okay.
in steady state condition, this steady state condition is saying that there is no change with time. Steady, do you understand the meaning of the steady state, right?
Yes, sir. Yes, sir. Yes, sir.
During
When
that,
transient is end, sir.
uh,
Transient is end.
yes, during steady state condition, it the carrier concentration doesn't change with the time. Okay, so that is the
Okay.
steady state condition. If it is in steady state, there is no change in carrier concentration with time. So this will be Q. Okay,
Okay, sir.
okay. So or
Okay.
if we are going, this is the complete thing. Okay,
Okay, sir. Okay,
in
sir.
with continuity equation, what we are trying to find is we will find some excess carrier concentration, and with the excess carrier concentration we can find the diffusion current, right?
Okay, sir.
Because excess whatever excess carriers are there, they will diffuse from the higher concentration to the lower concentration. Okay, when they move from higher concentration to lower concentration, there will be some current associated with them, with that,
Okay, sir.
right?
So, sir, in conclusion, we can understand the extra excess carrier concentration inside the semiconductor. For that, the uh, how much diffusion current is there.
What is there? There will be diffusion current, and one more thing is, so whenever access carriers are generated when you are applying some field, when there is application of field, when there is application of light, and all these things, right? Okay,
Yes, sir. Yes, sir.
okay, and the steady state comes when there is a no time dependent. This is the time dependent access carrier concentration. Okay, this thing.
Yes.
Okay, this is the uh, distance dx with dx. This is the concentration gradient. Spatial access carrier concentration. Spatial access carrier concentration is uh, you have a semiconductor, and how these uh, uh, there is some excess carriers are there inside a semiconductor and how they are diffusing inside a semiconductor. That is what it is given by this. Okay.
Okay, sir. Okay.
And this is the field. If you have applied the field along with the this, how the carriers are moving with the application of the field, it is given by this. Okay. And
Okay, sir.
this is the generation inside a semiconductor, whatever, wherever we don't. Okay. And this is the
Okay.
excess carrier recombination in the semiconductor. In the whole semiconductor.
Okay.
These both are for the whole semiconductor. Okay. Now let us go in these are two these things, two graphs, right? Let us go in this one first. Okay. So we will discuss this one only and then we will leave. Okay. These two things we will discuss too. Okay. So now let us say you have a semiconductor, piece of semiconductor, and you have shine the light at this end. Okay. And
Okay.
and in some time it will come in a steady state. Okay, you keep shining. After some time it will be in steady state, right? And that steady state, you just keep shining. There will be a in steady during steady state, as much as carriers you are generating, the same number of carriers will be recombining. So that is the steady state. Okay. So
Sir, this is a condition for steady state.
huh?
Number of carrier generated equal to number of. This is a condition for steady state. Number of carrier generated equal to number of recombination.
Yes, because at that time only delta n will be zero because the delta n will be, this is the excess carrier concentration will be constant at that time.
Okay, sir.
Okay, generation will be equal to the recombination during that one. Okay, that is the same thing. Okay, because of the shining of the light.
Okay.
So the
Okay,
steady
sir.
state comes. Okay, so this component is the so you have shine the light at this point. Okay, the excess charge carriers delta N and delta P are generated in this region. This is, let us say, P-type semiconductor. Okay, so delta N and delta P are generated in this region. So here are the excess electrons and holes. So which is the Pn is greater than Ni square. Okay, so they will try to recombine, but P, Pn is equal to Ni square, it will be there. So greater, just give me 1 minute. Mm, Pn is greater than Ni square, they will try to recombine, but uh, at the same time, here the concentration N is more, P is more in this region, and in this region it is less, so it will diffuse in this direction, right? What's the point? I
Yes, sir.
just want to try. I just
Yes,
want to
sir.
try this.
Want to you just want to tell that when light shine on a particular edge, there will
Mm-hmm.
be excess carrier is there,
Mm-hmm.
and and the opposite part will be the carrier will be less.
Mm-hmm. So
So
they
there
will
will be a
diffuse.
concentration gradient is there. Concentration gradient is there. So diffuse current is there.
Yes, yes. This is what I want to tell. Okay. So,
Yes, sir.
and this is the field part. We are not applying any electric field, that is zero. Okay. Generation is not there inside the semiconductor. As it reaches to the steady state, it is zero. Okay. We are generating at this point. Okay.
Sir, which point, sir?
At,
Green
at,
graph.
at this one. So what we are trying to find the concentration or the or how the electrons and holes are diffusing in the x direction, x. Okay, so in this region the generation is zero, generation rate is zero because we are not generating the carriers in this region. Okay, So, but
Towards X, no sir.
huh?
Towards X.
Yes, yes, yes. Okay, and this
Okay,
is
sir.
the
Okay.
recombination rate. Okay,
Yes.
so carriers are diffusing here. So in this region, carriers are diffusing, right? So Pn will be greater than Ni square, right? Because P and N here carriers will be more because they are diffusing. So they will recombine.
Okay.
Recombination will be there. Okay. So
Okay.
this equation for this condition, whatever I told you, will reduce to this equation. Okay. All other parameters are gone.
Okay, sir.
Okay. So
But sir,
mhm,
uh, but uh, but sir, if I put here del, acha, okay, del by del x of del by del n. Okay, okay, okay.
mhm.
So there will be square. Okay, sir. Okay, sir. Clear, sir.
Okay.
Clear.
Yeah.
Yes, sir. But sir, there will be a negative sign is not present, sir, because if I differentiate this will be again go to the right side.
But that is the excess charge carrier concentration.
Okay, 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 okay. This is due to excess charge carrier.
Yes, this is the excess charge carrier concentration. So this will reduce to this one. Okay.
Okay,
So
okay. This is the general solution, sir. General solution. I
this
think.
is the solution to this differential equation. Okay. So
Okay,
if you plot this, and it will give you this sort of results. Okay. So
okay.
solution to this one is this purple color. Okay.
Purple one.
Yeah. If
And what is the green one, sir?
this x is long enough, this x is long enough.
Okay,
Okay. If your semiconductor is small, then it will vary with these green, black, and all these things. Then
so sir, if the channel is long, then purple is happen. If the channel is moderate,
hmm.
then black is happen. And if the channel is very small, then
Yes,
green is happen.
yes, yes.
We have to remember the formula, sir.
If you can remember, because there was one question.
No,
Okay, what you can do is during that your examination, that will be, I think, sort of open book exam, right?
no, no, sir.
So, okay, you have to go to the center.
Yes, sir. Go to the center, sir.
Okay, 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 okay. I don't know that. So,
Sir,
so, so you have to
I think, sir,
remember.
you have also make the question, sir, because every that told that every teaching assistant will be make the question.
No, actually, whosoever is teaching online, taking online classes is not making the question.
Okay, okay, okay,
So
okay,
there are several TAs who are taking some online classes, like the live classes, and there are some TAs on the back end. They are making the assignments and questions.
okay, sir. You are not responsible for any kind of question making.
No, no, no. Okay.
Then, sir, it will be difficult for us, sir.
No, it would be. You should know the basic
No,
concepts.
sir. Actually, sir, we have to. I don't know what about the other candidates, sir. Actually, sir, we require the sir certificate, nothing else, sir. We have to know the concept. It is very urgent, sir. But
Mhm.
sir, the course pace will be such that sir, 4 lecture, you have to teach something, okay?
Mhm.
And it is, and we have already working profession, sir, and
Mhm.
there will be a lot of pressure regarding classes, sir.
That I
Okay, sir,
know.
no issue, sir. No issue,
Okay.
sir. Okay.
Okay.
Sorry, sir, for my own problem discussion.
No. Okay. So here, the same thing is there. I just spread it out and with the every component. And this is another example where what the light is shining on this semiconductor material. Okay, the whole semiconductor material is we have shining light on the whole semiconductor material, and charge carriers will be generated. Delta N will be equal to delta P. Okay, that is there. So this is the like steady. We are continuously shining the light and it will reach in some steady state. Okay. So
Yes.
uh, during that time, during steady state, this will it will go to zero, and because this is it, and everywhere light is shining, so delta N is equal to delta P everywhere throughout the semiconductor. Okay, so there
Okay, this is
won't
some different case, sir.
there won't be any diffusion because there won't be any carrier concentration gradient,
Gradient,
right?
gradient is there.
So this will
Yes,
also
sir.
go to zero. Okay, so and at this point we haven't applied any field. So at that point, the generation rate will be equal to the this recombination.
Combination.